So now the network is getting created, the blockchain network. That means every node is getting boot up for the Ethereum network. So it will take some time. So this testbed is considering mainly the research perspective, not for developing the enterprise applications. So now the setup is done. So now we can monitor. So it may be like I can also join the network remotely wherever I am into. I can join into the network. I can deploy the smart contract using the remix. But anyway, it will be connected with ours, not the mainnet of Ethereum. And we can monitor. So for example, I want to see the power statistics. So we can see right now we have the power tool enabled, sorry, the device enabled on only one Raspberry Pi. So this displays how much power is consumed by that particular Raspberry Pi device. So this will be very much useful when we are presenting our result. So then we can go to Grafana. This is the open source we are using. So we can go to Grafana and see the statistics. That is the number of blocks mined, and I think I am this. So this shows the CPU consumption memory of each and every nodes that we can choose here, but this takes some time. The data has to be loaded. Also, we can. So right now it shows that there is no block on the server one, but it will get loaded after some time. We can see how many blocks are with so and so nodes. So all those informations we will be getting, the transaction rate, pending transactions, how much memory is getting used. So these all will be very much useful for providing us a result in the paper. So we have the complete setup. As a user, you have to only deploy the smart contract. Even some example smart contract also will be giving, and we are going to provide certain standard way of writing the function so that it will take less computational complexity or the storage complexity. So this can be accessed through nsc lab.IITA.ac.in. It's open, anybody can use this testbed. And this is part of the project funded by Department of Science and Technology. So in case you have any issues or any queries with this, then definitely you can please contact. So once we are closing that, it should be like we have to close the network so that next person. So it's like when you are using, complete setup will be given to that particular user. And let's say that you have used now, later you want to roll back, that facility also we are providing. All your data will be brought back. Let's say you have mined some 10 number of blocks, or let's say up to 1000 blocks it is done, and you want to continue maybe tomorrow, then from 1001 it will stop. So while implementing this, we have find something like, if it's the browser based interface, if the browser won't get any response from other nodes in 2 minutes of time, then it closes the connection. So what we are doing is we are sending the fake packets or the dummy packets, and we are removing that if there are no packets to send. So this is about the test bed what we have. So you are always welcome to use this too. So now let's go back to the slides, which is on the transactions, consensus, and the digital signature. So we have discussed about the transactions in the previous session also, considering the Bitcoin. So it is applicable for any of the blockchain implementations, because transaction is the one is going to provide the activity or the action in the blockchain network. If there are no transactions, that means no activity is happening. So the activities are to, in general, I say the activities on the blockchain is like, we want to update something, or we want to insert or create the new things. And next one is the read only, we just read. For example, if we take the database, we do update, we do insert, we do read. However, we have delete also, but in this case, we don't have the delete option. But anyway, now people are talking about the redactable blockchain, because by mistake we put something, it may be confidential or incorrect one we put, we should be in position to roll back that. So that's why now people are talking about the redactable blockchain technology. So if we see these are the activities, what are the things that are going to be covered under the transactions, are like it does the update, insert, or create. So here update, what I mean to say is we are not going to change the data, whatever is already placed in the blockchain, because that's not allowed. That's the reason we go for the blockchain technology. So update means I have the transaction account balance. I want to make some transaction so that my account balance get credited or debited. That's what I mean to say as the update. And next is I may do some insertion like creating the new account, or it may be like adding the new transactions. So these are the activities that can happen as a transaction. So in case of read only, for example, I want to find out the account balance. That is the get function, we can say. Get account balance or get the block details. So these things are considered as the read only. Those are not part of the transactions. So this is the sample transaction of the Ethereum. So we can see. So it contains the block hash. So it refers on which block it is going to be added, and what is the block number, who is making the transaction, and to whom it is going, and what is the gas price, because in Ethereum, gas is the one used to control any kind of, we can say, looping attack or infinite looping attack, sorry. So this ensures the halting. So that's the reason the gas is used, and the gas will be having the equivalent ether price. So that price is given in the gas price. And the transaction hash, are we sending any input? So that means input refers are we sending any message? When we are sending, for example, money, we mentioned that some remark. So for that, and this nonce is used to find out what is the transaction number. For example, if I make hundreds of transactions, so when I'm going for 101 transaction, so here it will be like 101. And the same number will reflect in the blockchain also, in which the account number and the account balance and number of transactions. So there also it will reflect. That is, it is in the world state, so that anybody can verify whether the same transaction is spent more than once. And these two are the digital signature, R and S. You remember in the segregated witness, we are talking about the two parameters, R and S. We'll see how these two are getting computed. We can see an example. And this is the to address, the transaction index, and this V, because as we have seen there also R comma S and R comma minus S, both are valid, and definitely only one is chosen for signing. So we have to find out whether this one or this one, that can be identified through this V, and the value is the amount how much we are transferred. So this is done within the private network in my machine setup. So don't consider that this value is too high. So the blockchain technology, as I mentioned already, and even someone also asked, cryptography plays the major role. So one is the public key crypto system and the hashing. So the intention of using the cryptography there is for two purposes. One is for integrity, and another for ownership. However, people ensures the confidentiality in certain implementation, but those are like we can keep aside now. So those are not required. Maybe it will be discussed in some of the other lectures. So for the integrity purpose, we use the hashing. So which takes infinite size of output. Infinite means definitely there is a size, but that size is huge. It takes the infinite size output and produces the fixed size output. It may be 256 bits output or 160. It's up to the algorithm what we use. That's the cryptography algorithm. And how it ensures the integrity is, let's say this is the message I have, and I computed the hash. The message is of some infinite size. I computed the hash of it, and it produced the fixed size output X. And I'm keeping X with me. And I am sending the message to the third party. It may be the cloud or whatever it may be. I sent. Later, I requested the cloud. I'm not having this M now. I sent. Now I request the cloud to give me M. Now M comes to me. How do I ensure that cloud has not modified that? So what I will do is I will again compute the hash of this, and I will map whether both are same or not. So let's say if this is of 1 KB and this will be only 256 bits. I keep only 256 bits with me, and I moved 1 KB to the cloud. It may be 1 KB or TB also, we assume. And then once it comes, I compute the hash and I do the mapping of only 256 bits. If both are same, then I know that the data is not modified, that is M is not modified, otherwise it is modified. So this is the way hashing helps to ensure the integrity. And for the ownership, we go for the digital signature. So the digital signature is done by using the public key crypto system and the hashing. So how it happens is, let's say if this is the message I want to send to someone, and the opposite, that is the other side party, should ensure that I am the one sending the message. So what I will do is I will sign the message by taking the hash, and that output will be encrypted using my public key. And this will be sent to my other party, that is the receiving party, along with this M. In case we need confidentiality for M, that's different. This has to be encrypted. Anyway, now let's assume that it's going in the plain form. Now, once on the receiving side receives M, sorry, here it should be private key. I missed this. I'm extremely sorry. Because for signing, the encryption should be on private key. For confidentiality, the encryption should be on the public key. So using the private key, I have signed and sent this message to my receiving person. Now what the receiving person will do is, after getting the M, he or she also computes the hash of this and then decrypts using the public key of mine, because public key of mine is already shared with that person. So whatever sent by me as a signature, that gets decrypted using my public key, and this will be producing H of A. And now these two will be compared whether both are same or not. If both are same, so that means the message is accurate, as well as it comes from so and so source, because he has signed, because he is the only one having the private key. However, there is no guarantee whom he is claiming is he or not, or she or not, because anybody can say, let's say I claim as Alice and send you the private and public. You cannot find out. So that's why we go for the digital certificate. Who will be issuing is the certificate authority. But anyway, now they are trying to bring blockchain technology into that also. So this is the way the cryptography is getting used in the blockchain. So how hashing is used? Let's say we are saying the blocks, the hash of this is available here, and the hash of this is available in the next block. So this is the way the hash is getting used to ensure the integrity. And for the digital signature, whenever I am making a transaction, I should make sure, or my verifying party or validating party should make sure that I am the owner of the transaction or owner of the coin and spending it. That can be verified through the digital signature. So for these two purposes, cryptography is getting used. As I said already, there are implementations like Monero. They are ensuring the confidentiality also. For that, it's only the symmetry, even symmetric crypto system also getting used. So how the ECDSA works, just we will see a brief example. I will not go much in detail. So there will be a curve. Most of it is elliptic curve. There are different curve is getting used, but Bitcoin and Ethereum uses SCCP2K56. I may be not accurate with the name. So this is the curve it is getting used. And it has the base point G, which is the vector value, that is XY coordinates, and N is the order of the curve. Again, this is like the scalar value. So what we have to do is, let's say these curve parameters are decided. Now, these are like, we can say the public curve parameters. And now, let's say I am the owner. I want to create a key pair, that is the private and public key pair. I choose a random number, which is the scalar value, that's between 1 to n minus 1. And I compute the public key by doing the point doubling. That is, I multiply this DA, private key, with the base point, and it will be again producing another point in the curve. So here it is given as multiplication symbol, but in elliptic curve, it is considered as point addition and point doubling. So this is my public key, and this is the private key. I give my public key to my the receiving parties for validating my signature. So how the signature is generated is like, as I said, first we compute the hash, and then we go for applying the encryption techniques. So here what happens, first we, let's say M is the message we are going to sign, and we compute the hash of that output is in E. Now we choose Z be the leftmost bits of E, some number of bits only we are taking, and Ln is the bit length of the group order, and we are not taking more, because it should not go beyond n value, otherwise will not be getting the output what we are deserving, because it should be always in the less than n, because we are going to compute the modulus. So then we have to select a secure random integer k, which is between 1 to n minus 1. This is like again another secret key. Then we compute the curve point as we have done for computing the public key. then we say there are two values getting computed. One is R value and then the X value. So R is computed from X coordinate, X1 mod n. If we see R is 0, then it has to be go for another coordinates we have to choose. That means we have to choose another key. Otherwise, we'll go for S. S is the K inverse. This is the secret, which is inversed, and it is merged with, or we can say multiplied with the Z, which is the actual hashed message, plus the X coordinate and the private key, what we have already generated. So if this condition, if S is again 0, we'll be going back. Otherwise, now this is the key. You remember in the previous session also in segregated witness, we discussed about two parameters R and S. Even a slide before this also we are talking about those two parameters. So these R and S are considered as the signature of this particular message. And now this DA ensures that I am using the private key of mine to sign the data. So on the receiving side, we are going to verify. So while verifying, we have to make sure that R and S are between 1 and n-1. Then again, the message also comes with the digital signature. We see the message, compute the hash of it, and again we take only those leftmost bits. First, we compute W, which is S inverse mod n. Yes, because it comes from the center side. And we compute U1 and U2, which is ZW. So Z we know because that is the leftmost bits of the message, that is a hash. And U2 we compute. So Z is known, W is known, R is known, and then W is known because R is also coming from the center side. So then we calculate the curve point x1, y1 based on this equation. And if we see x1, y1 is the point of infinity, then we say the signature is invalid. So the point of infinity is considered, let's say this is the curve we have. If we draw a line that is always touching, we can say 3 points in the curve. But if we write the parallel lines, then it will never touch. It will touch only twice, not more than that. So we consider that it will be touching at any point of time. So that we consider as, but it is not going to touch, but we consider that. So that's why we call as the point of infinity. So that point of infinity is the value which is beyond that order values. So if it is so, then we say it is invalid. Otherwise, we say that it is valid if this one is satisfied. That means the X coordinate which is computed is equal to R. Because here if we see the X, that X comma Y, that X coordinate is the R value, what we are having. So if we actually see this, what happens is the proof, we can write like this: U1 into G plus U2 into QA, and we can say this U1 into G plus U2 into QA will be considered as what we have done, DA into G. That's what, because this is the public key what we have computed, that is through DA into G. So now we can write this as U1 plus U2 DA into G. So we can write like this. Now, if we go for U1 and U2, so U1 we know that is, see, actually I am unable to write this completely. I can directly take you to the Wikipedia. So we can see in this. So we can write like this. After that, if we see the U1 and U2, so the U1 is, that is Z inverse, U2 is RS inverse. So that we are applying. After that, we are taking this S inverse common. And if we see Z plus RDA and S inverse also, whatever is getting computed. So the S inverse is K inverse plus Z RDA. So that is applied and these two gets out. And this K inverse, again we are taking inverse, so we'll be getting K as the value. and we are multiplying with the base point, which is kg. And if we see r is, the x value of k into g. So with this, we verify that the sign done by so and so person is correct. Otherwise, we say it is not correct. So this is the way the elliptic curve digital signature algorithm works. And now I have signed, but how do you ensure that I will be the one, or the signature and the addresses are linked? How we will check that? Actually, what happened in case of Ethereum, we have this R and S. Elliptic curve is having the feature with the R and S. It is possible for us, any verifying party, to bring the public key of the sender, that is, or the signer. We will be knowing the public key of the signer. From this, we can bring out. So once we know the public key, and from this we can derive the address, as we have seen in the previous session. And this address and the from address of the transaction, these two will be compared. If these two are matching, then we know that the respective owner is spending the coin. Otherwise, it is someone else. So we consider the transaction as invalid. So the network is, so as of now, we have discussed about the transactions and the digital signatures. Now we'll be moving on to the consensus protocol. So as I said, or we discussed, or we all know, the blockchain is following the distributed ledger technology and distributed systems. So there will be multiple parties involved. But when we are talking about the distributed system, there is an issue of consensus. The consensus is coming to the common goal. That is, we have to reach the agreement. So if there are n number of users, then it is very, very hard to ensure that. For example, if we see within a classroom, if we want to elect a leader, even though there are more than one contestant, so the teacher may ask who will be voting for whom. So then the students will raise their hand, and directly we will see and come to the conclusion that the teacher can take the decision. But here what is going to happen is, people are located in different places. In that case, how we are going to reach the consensus? So that is always the problem in case of the distributed systems. So these we have already discussed. And now the another question comes. One is reaching the consensus. Who will initiate? That is, something has to be proposed. Who will be proposing that? Will it be the client or someone else take it forward to propose? And if someone else has to take it and propose, then why should they do it? So these are the question comes. So one is, we need the consensus, and another one, why the nodes should participate in reaching the consensus. So we consider two types of network, permissionless and permission. In permission, it will be mostly on the enterprise applications. Their nodes are like, they are forced because they are under an administrator. So they will be forced to do that, or they do the voluntary job. But in case of permissionless, people will not do, because the world is completely the business world. They always see, if I get something, then only I will do the task. Otherwise, I will not do the task. So these are the issues we face when we are going for the distributed systems. So to reach the consensus, or what we call as the consensus, is first is the termination. So what we say, every correct process, whatever the nodes running in the network, all the right nodes or the genuine nodes decides on some value. So that's the first requirement. Second, if all the correct nodes propose the same value V, then any correct process must decide. So let's say if I am the right person and I have decided yes as the final decision, then every right process will say as yes only. And next is agreement. Every correct process must agree on the same value. So these are the things that should be ensured to reach the consensus. Why consensus is a problem? So this is considered as the Byzantine fault. Based on this, the problem was explained. So let's consider that here we are having only 3 nodes. Let us consider there is a commander and there is a lieutenant 1 and a lieutenant 2. They are going for a war against a country, and there are 2 units deployed, because they cannot be in the same place to attack the country. They have to be in 2 different places. However, they will be performing the attack or going for the attack if the commander gives the command. So let's consider it, they all are in different locations, not in the same location. So now commander has decided. So there are 2 messages he can pass. One is the attack and another one is the retreat. Okay, don't go for attack. Okay, so that's what the commander can pass. So the commander sends the message to both the lieutenants, you go for the attack. Now these lieutenants will see the majority. So now the once the commander sent the message, in traditional army, if we see, once the commander says, then they follow it. So that's different. So we will not bring the same into this. We consider the scenario that demonstrates the problem of the agreement or reaching the agreement. So the commander sends the message as attack to both the lieutenants. So now lieutenant 1 receive, let's say attack means 1. Then retreat means 0. We consider like this. Now we say that to the commander says to the lieutenant 1 as attack. So that means he has 1 into his record. Lieutenant 2 also has 1 into his record. Now these 2 parties are going to exchange their messages. Let's say now the lieutenant 1 is the genuine person. He says, I received the message from commander as attack. So he is having 1 more message as attack. And lieutenant 2, let's say he is compromised or she is compromised. So they are sending the message as retreat. That means 0. Now you see the lieutenant 1 is not in position to take the decision, because it's both are 50-50. There is no majority. And let's see the another scenario where the commander is compromised. Commander here says attack and here says 0, that is retreat. Now these 2 are exchanging the message. Lieutenant 1 sends the message to Lieutenant 2 as 1 and Lieutenant 2 sends the message as 0. Now also these 2 parties are not in position to take the decision. And another important problem is Lieutenant 1 is not sure now whether the problem is with the commander or the Lieutenant 2. So this is the issue. We cannot reach the majority. Anyway, if we go for digital signature, so the problem gets solved. But to demonstrate the problem, this is the example. Now let's see that there is 1 more lieutenant. So we have lieutenant 3. Now they are also exchanging the message. Now what is going to happen? Okay, we consider in this case. Okay, here also we can consider. So we don't consider now. So here, because commander can give maximum of any of the 2. So they cannot give more than 2 messages. So that's the assumption we are keeping. So here attack, retreat, and then attack. So now 1, 0, 1. And when the Lieutenant 1 is going to get the message from Lieutenant 2 and 3, then it becomes 0 and 1. Here it becomes 0, 1, 1, because 1 and 2 is going to give us 1 as the message, and Lieutenant 3 will be getting 1, 0, 1. Now if we see, there is a majority. So now all of them, even though they are not, we can consider that earlier case Lieutenant 2 was compromised, but now they are not compromised and commander is compromised. However, these people are in the position to take the decision based on the majority. Now you see how many nodes are here. It is 3 nodes are here in this case and 1 node failure, that is 1 faulty node. And here if we see, there are 4 nodes and there is 1 node faulty. So here we are not in position to take the decision. However, here we are in position to take the decision. So let's derive a simple metric. Let's say if my network size is n, which is equal to 3f plus 1. So what is this? F refers number of faulty nodes in the network. So now in this network, that is the second one, if we see the number of faulty nodes, that is only 1 faulty node, which is considered as the compromised node, plus 1, which is 4. If the network is of size this with this faulty node, then we will be in position to take the decision. However, here if we see n is 3, and if n is 3 and there is 1 faulty node, then we are not in position to take the decision. So what this equation says is 2/3 of the majority in the network should be genuine. So in that case, we can reach the consensus. So this is the Byzantine fault, and the solution which is provided using this equation is called as the Byzantine fault tolerance. And when it comes into the implementation, we say that as the practical Byzantine fault tolerance. So this is one of the consensus protocols, and from using this Byzantine fault tolerance, there are so many variants derived out of this, because here we say 3f plus 1, people try to further reduce with the 2f plus 1 also, and the 2f or 1f plus 1 also. So we have also done some work in modifying this. So that's the first problem, and we have the solution with majority, and this is another problem. We don't have any solution for this. So the problem is the 2 generals problem. Let's assume don't bring too much logic like we have Wi-Fi, those things and all. Consider we have the physical communication only. The person from this to this, they have to pass the messages. Let's say there is an army unit by A, which is deployed in both the side of the country on which they are going to attack. And they have not decided the time on which they have to attack. So it's like now unit 1 commander decided, let's go for the attack at 1:30 p.m. We consider that the time is also synchronized. Now the A1 sends the message to A2, that is sending the person. Now can you say that after sending this message, see, very important thing, if both the units go together, then they can win the battle, otherwise they cannot win the battle. So they have to ensure that A1 has to ensure that A2 is also coming for the attack, and A2 should also ensure that A1 is also coming for the attack. Now if we see, A1 sent the message to A2, now can A1 go for the attack or not? So this is the question I am asking.
You can raise hands if you wish to answer. We will unmute you, or you can write on the chat box.
Just think of this, whether we can do or not. that is A1 can go or not. Just think of. So there is one message I could see. No, because there must be a consensus. Okay. So the remaining are not getting any thought whether can go or not, or may not be interested. Actually, A1 cannot go because there is no surety on A1 side that the message received to A2 or not. So when it is possible, let's say there is an acknowledgement from A2. Now, in this situation, now can A2 go for the attack? Can A2 go for the attack in this case? So A2 cannot go because the reason is A2 is not sure whether A1 received the message or not. So what is required? Another message. Now A1 can go for the attack or not. Again, A1 cannot go because A1 is not sure whether this one reached here or not. So this will be keep on going. And this problem is not solvable. However, people say that TCP protocol, I hope we all have gone through in our UG. So which does SYN ACK and then ACK. This solves the problem. But again, if you go for FIN, here also there is no guarantee. Because if the acknowledgement packet is lost, there we are considering, we are resending the message for some time. After that, if there is no response, automatically we are closing the connection. But in this scenario, we don't have the option. So there is no solution for the two generals problem. But how the cryptocurrencies or the blockchain implementation like Bitcoin and Ethereum are solving this is because of the Bitcoin proof of work. What they say is, you send the message, wait for some time. Okay, in that duration, it will be clear whether it is reached or not. So the intention in case of cryptocurrency is, I created a block and I sent to my neighbors, but I want to ensure that whether it is reached all the nodes in the network or not. So you have to wait for that. So when you are waiting, that means you are solving the proof of work. It takes another 10 minutes. So those 10 minutes are like average 10 minutes are sufficient that the blocks are getting distributed across the network so that we can reach the majority. That means majority of the nodes accepted so and so blocks. So when we talk about the consensus, why it is an issue? It is an issue because if somebody misbehaves, so then only we are not in position to reach the consensus. So there are two faults we face because of that consensus is an issue. The first one is the crash fault. And the second is the Byzantine fault. So the crash fault is the one, let's say that we all are genuine users of the network. And I have asked the question, let's assume that we all are genuine. Let's say you are sending me, or I am asking you to answer so and so question. So based on that, we will see if the majority says yes, then that is yes, otherwise no. Let's assume that you are the genuine person, but your acknowledgement is not coming to me, or your opinion is not coming to me. What would be the reason? You are genuine, but your acknowledgement is not coming to me, or that is your opinion is not coming to me. What would be the reason? So we can say the network fails or your system fails. So that would be the reason in which I am not getting, but you are genuine. So this is called as the crash fault, which happens due to some unavoidable circumstances. So one problem is crash fault, and another one is the Byzantine fault. So what the Byzantine fault means, the attacker is like the person is having the malicious intention. That means he could perform the attack. So that's why he is not sending the message, or he is sending the wrong message. So these are the two faults we face in the distributed system. So in crash fault, it is not an issue that can be solved very easily because there is no malicious person involved. However, in Byzantine fault, we have the malicious person. So there are consensus protocols considering the crash fault as well as the Byzantine fault. For example, Raft protocol is based on the crash fault because there will be a leader, and leader tells to all the followers that this is the one we have to follow, and they all accept. But in case of Byzantine fault, that won't be applicable because there is a possibility of the malicious users. And now next thing, we talk about the permissioned blockchain. So in case of the permissioned blockchain, we allow only parties who are known. So that means they don't misbehave. So if that is the case, when we are going for the consensus protocol, only crash fault based consensus protocol is required. We don't want Byzantine fault tolerance or Byzantine fault based consensus because we know all of them and they don't do any mischievous activity. So Hyperledger was considering that they used the Kafka protocol, but there is always possibility of the insider attack. So maybe some are not happy and they are compromised. So considering that, we should go for Byzantine fault tolerance in that case also, even if you are going for permission. However, Hyperledger Fabric gives us the provision to plug in whatever consensus protocol we want. So now considering this, we have the consensus protocols, and those are of two types. One is the probabilistic and another one is the absolute. So probabilistic refers that, or I can say instead of absolute, it is the finality. So it's like in case of probabilistic, if we decided something, or if I decided something, there is no guarantee that that will be accepted by all. That's why it is probabilistic. Something else may be accepted. Because of this reason, only the forks are getting introduced. And next one is the finality. If I decided something, that will be final. Okay, so there won't be any alternate for that. So this is considered as the finality consensus protocol. So the proof of work, proof of stake, all these things comes under the probabilistic, and the PBFT or the variance of this comes under the finality. So now let's see briefly about the proof of work consensus protocol, and then I will explain this table. So what the proof of work is, it's simply a hash function, nothing more than that. We are going to solve a puzzle using the hashing algorithm. So what it says is, let's say I said there is an input and output. There is a function f, and this function f is the hash function. And this output is having some size. That means the range. For example, let's say this is the range. This is starting point, and this is the end. Or we can consider if the function is 10, like this, percentage of 10. Now we know that the output will be from 0 to 9. So similarly, we have some starting point and the end point. And what we are saying is, while solving the problem, the proof of work says, you find out an input, you find any input. but it is not any input. There is a constraint that I will come later, and let it produce the output. And when it is producing the output, definitely it will be belongs to any of this place. It cannot go beyond, because this is the starting and ending. There is no other option. Now the puzzle is, I put a cutoff here, which is called as the target. I say that you find out the input, give it to the hash function, let it produce the output, but that output should be in this range. If it is coming here, then that input is not accepted. But it can lie in any of these places, but I say that it should be within this range. So this is what the puzzle is. And if I try the input one, it may not lie here, it may come into this place. So then I go for the next input, then again it may come. The third input may come into this place. So now I am success in solving the puzzle. So I give that input to my neighbor, they compute the hash and they say it is part of it. But that's not so simple, because the size is too big. It is from 0 to 2 power 256 minus 1. This is the range. And I put the target here. And what is the input in case of the blockchain? We have the block. It contains certain parameters. So now we see the input, whatever to this hash function, as two parts: static and the dynamic part. So in case of static, the attributes whatever present in the header of the block, excluding that nuns, which is or which are going to get updated. Other than those, these will be part of the static. Otherwise, when we are solving the puzzle, we can bring any value and we can say the puzzle is solved. So we have to make sure while solving the puzzle, it is also including the block data. And the dynamic part, because if we are taking everything as static, so the problem with this hashing algorithm is, if we give input 1, it produces x. If you again give the input 1, it will produce the same x. So the algorithm is deterministic. That means whatever number of times you are going to give the same input, the output will remain same. So now if there is no dynamic part, if it is only static, what is going to happen is, Neela madam, I'm sorry, the session is up to 2:30, right?
Yes.
It's up to 3:30.
Yeah. 2:30. Yeah.
Yes. Thank you.
So you can also have a brief, like a pause. You can give a brief break. And if you wish to take questions now, you can do that.
Oh, it's okay.
Whatever you think, I mean, this your own way.
Okay, sure. Okay, thank you so much. So in case if we are considering only the static input, what is going to happen? I give the input and it produces the output which does not lie in this range, which lies in this range only. Then I don't have the option. Whatever number of times I am going to give the same input, I am into this range only, and I never solve the puzzle. So that's why we go for static and the dynamic. And I will tell what will be the dynamic. So now, how first I take these parameters. In case of dynamic, I am giving the value as 1. So for example, let's take AsiaNet as the static part and the dynamic part as 1. Now this will produce some output which may not be in this range, so it's going beyond the range, so we reject. Then I take 2. Now what is happening? The input is getting changed. Now 3, 4, 5. I will go up to the time I reach this output range. So let's say, and this is having definitely certain size. Let's say it is 16 bits. And we know if it is 16 bits, it cannot be more than 65536 as the maximum value. Then again, I will start from 1. When I am starting from 1, since the algorithm is deterministic, I am doing the useless job. So that time what we can do, the static part can be modified. How we will modify? The transaction route we cannot modify, the previous hash we cannot modify, but the timestamp can be modified. So we were solving the puzzle for last 20 minutes or 10 minutes. It is not solvable. So we change the timestamp to the present one, then again we stop. So the static is now changed and the dynamic will start from 1. So it will be like 1, 2, 3, again will be continued. So definitely at one point of time, we are going to get the input which will be in this range. So this is what the proof of work puzzle solving is. And now this dynamic part is part of the block header. So what is going to be here? Let's say now when I am changing my dynamic part, so the value is, for example, 1000. With this, I solve the puzzle. That means the output, it comes in this range. Now, like I solve the puzzle and I will give to my neighbors. And now my neighbors should be in position to verify that. They could not solve again those many number of times. They have to solve, they have to verify in only one attempt. So it's like to solve the puzzle, you need exponential time, but for verification, we need constant time. So how it is possible? We are going to give 1000, this value also in the block header. This is called as the nonce, which is number 1. So you remember when I was showing the block header, there was a field which is nonce. However, there is a difference in computing this value compared to Bitcoin and Ethereum, because Ethereum want to ensure the ASIC resistance, so they go for memory hard process or memory hard algorithm is getting used. Okay, so but anyway, let's understand that this nonce. So now once this block goes, the receiving party take this value, concatenate with this value, and they compute the hash and they find out that it is less than this, within this range. So now the problem is validated. So in one attempt, it is done. That is in constant time. So this is the way the proof of work works. So everybody will be trying. And now why we can say it is named as mining, we are trying to find out this value. So we are digging to find out. That's it. So you may think that computing the hash function needs very, very less time. That is also true. It needs very, very less time. But why we say it needs 10 minutes time to solve the puzzle? So I did a small experiment with my machine, which is of 3.2 gigahertz processor having 4 cores. I wrote a Golang script which parallelly runs the 4 process and trying to solve the puzzle. So I have given the static input, like let's say there are 4, 1, 2, 3, 4. The static input is something like X. And here I started from 1 to some value and some X. Here this is going to start from, that is the nonce value, from X plus 1 to Y, and Y plus 1 to Z, then Z plus 1 to some number, it may be ZA. So this I was running, and the target I have fixed, this threshold I said, right? So this is called as the target. Let's see how this is getting computed in the next slide. So this target, so the algorithm will produce the output between 0 to 2 power 256 minus 1. So the first target I put is 2 power 250, and that took 0.328 seconds to solve the puzzle, and it made 1033 attempts. So when I go for 2 power 240, it took 0.356 seconds, and these many attempts were done. And when I further reduce the target, that means when we are reducing the target, so from here, we are coming here, we are coming here, the range is getting reduced. So when the range is getting reduced, that means the complexity is increasing, difficulty is getting increased. When I am bringing this towards this side, then the difficulty gets reduced. So we can say if the target is more, difficulty is less. If the target is less, then the difficulty is more. And when I put 2 power 220 as the target, it takes 2 power 32 attempts, and in these many seconds, it could solve the problem. And next, when I put the target as 2 power 10, 2 power 210, I was unable to solve the puzzle. It was running for long time. and it could not solve the puzzle. I have to switch off the machine. And Bitcoin says that maximum target is 2 power 224, and it will be always coming down. And we want that puzzles to be solved in 10 minutes if I have to participate in the network. But you see, when the target is 2 power 20, it takes these many circuits. It will be definitely more than 10 minutes. So in that case, I cannot participate in mining the block. And let's say if we are going to apply this implementation in any of the constrained environment, that is the constrained infrastructure environment, then it is not possible to apply the blockchain technology. So that's the problem with the proof of work. And also this needs more computational power. It is going to consume a lot of energy. Considering all this, only the proof of stake was introduced, and that is taken by Ethereum now. So how the difficulty is computed in case of Bitcoin, how it is getting computed. So initially there is a target fixed. So that is the maximum target. It is fixed. And then we compute the difficulty considering the current target. So this we will come. And you see that there is a condition. Right now, if I am into some difficulty and I am adjusting the difficulty, when I am going to adjust the difficulty, it should not be like lower side or the higher side. That is, it should be like 1/4. We cannot go beyond that. Then it will be like very simple also and very hard also. That's the reason. So now, why this difficulty equation required? In Bitcoin, every 2 weeks or approximately 2016 block. It's not approximately. Actually, for every 2016 blocks, and considering approximately every 2 weeks, the difficulty get updated. So let's say they say difficulty as X for the next 2016 blocks, and they expect that to be done in 2 weeks. Let's say if it is done in 1 week, or we say that because it will be after the 2016 block, and if it is done in very short time, then what will happen is the difficulty will get extended. So because they find that the problem is simple to solve, so we have to extend the or increase the difficulty so that we will maintain, because they want 2016 blocks in 2 weeks. That means 10 minutes. If it is not possible to mine those many blocks, then reduce the difficulty, otherwise increase the difficulty. So we can see this equation. It says that expected time and the actual time. We expect 2 weeks, but it may be done in 1 week. So that is the deviation. That deviation get multiplied with whatever the current difficulty we are having. So it's going to increase. And then that increase means it is going to provide or needs more effort by the miners to solve the puzzle. So from the difficulty, we will compute the current target, which is maximum target by difficulty. And if you want to compute the difficulty, and we can see this equation. Okay, so it is like we can compute the difficulty from the current target, or we can compute the current target from the difficulty. So this is what applied in Bitcoin to update the difficulty. And do remember, in Bitcoin, it is updated after every 2016 blocks. But in case of Ethereum, it gets updated for every block. So I will not go deep into this because this may be discussed in Ethereum part. So they had 2 equations and the difficulty get modified for each and every block. But anyway, this is of no use now, I can say, because Ethereum has now moved to the proof of stake concept. And there, so what is the difference between these 2 equations is in this equation, if it is less than 10 or greater than 10. So if it is less than 10, something will be applied. Then greater than 10, whatever it may be, the difference is the same impact will be there. But in case of this next version of the equation, for every 10-second difference, there is a different impact is going to happen. That's the advantage of this metric, which is introduced in home state. And there is one more thing they have added, which is called as the logic bomb, or we can say it is the difficulty bomb. Sorry, it's not the logic bomb, it's the difficulty bomb. So let's say if they want to make some modification in the Ethereum implementation, they need time. That is they need more mining time so that it can be brought to all the users in the network. If the blocks are getting mined quickly, then it is very difficult to introduce that modification. So that's why they have introduced this difficulty bomb. When the block numbers are reaching more than this, it's like 1 lakh. Then what is going to happen is the difficulty increases. So it will take more time for the block to be mined. So that is sufficient for the developers to spread whatever the update they have made. So this is considering the proof of work. Now let's go for the practical Byzantine fault tolerance, as what we were discussing in the very beginning with the 3f+1. So what happens in this is there is a client who proposes and the request to the leader, and the leader has the replicas. So it's like we can consider in the network, there is a leader decided based on the voting mechanism. After that, whatever request comes, that comes to the leader. And even if the request goes to the replicas will forward that request to the leader. And first, the request comes to the leader. Then the leader sends that request to all the replicas as a prepare message. And then all of them are exchanging that message stating that I have received from the leader. So all of them are exchanging with all others. So after that, what they do, based on that request, they modify their database. So after modifying the database, see, they are not finalizing it, they are modifying. So the modified output, they are exchanging with all others again. So once they see the majority, then they finalize it and send the response to the client that now your query is satisfied or not satisfied. This is the way the Byzantine fault tolerance works. So here there is no need to solve any puzzle, but only thing is the communication between the parties. So to reach the consensus, I have to ask all the parties, and all those parties are also exchanging among themselves, then we are reaching the consensus. And here it is very much important. 3f+1 node should be there. Only f nodes are allowed to be the faulty nodes. If it is more than that, then we cannot reach the consensus. But if you see why it is not getting used in the Bitcoin or Ethereum, why they want to go for that proof of work, which is very complex. The reason is scalability. You see this connectivity. If we go for 1 lakh node, how much connection is required? That is how many communication is required. So it will be too much communication overhead. So that is the reason. If we see the number of accounts in Bitcoin or Ethereum, it will be in millions. So then it is not possible to do this. It's possible, but it will take a lot of time. So scalability is an issue. So, and you see all of them are communicating with all others. However, there are variants, so we'll not go for that. But this is what happens, and which is very, very complex. And because of this reason only, it is not getting used by the Bitcoin or Ethereum. But when we talk about the enterprise network where we know all our users and there are limited, then the practical Byzantine fault tolerance is better to apply. So this is another protocol which is called Raft. This is master-slave protocol. There will be a leader always selected, and whatever want to be decided, the leader will select and give it to the followers, and they all will agree with that. So you can see the communications here and the communication here is changed, that the number of communication. So this may also be used, but these are the crash fault tolerance, and it is not possible for the permissionless network to apply this. So the comparison, if we see, so there are different protocols: proof of work, proof of stake, delegated proof of stake, then practical Byzantine fault tolerance, and the ripple. So we can see there are two: probabilistic, and then absolute. So the proof of stake, proof of work, and delegated proof of stake, these are probabilistic consensus protocol. That means once, as I said already, once something is decided, there is no guarantee that that will be the final. So it is possible that something else will come and replace. However, in case of practical Byzantine fault tolerance and ripple, it is absolute. Okay, once we have decided, that is decided, no change on that. And fault tolerance, how many faulty nodes the network can survive. That is like, let's say we have 100 nodes in the network. Out of 100 nodes, how many can be faulty so that the network can serve very well for the genuine nodes. So here it says 50%. So here 50% means we cannot say in the count of users, we can say the computational power. If the 50% of the computational power is not with the attacker, then they cannot perform the attack, or they cannot disturb the consensus. So disturb means here they can say that they can take incorrect decisions and that will be accepted. So it's based on the computational power. However, here in all these things, we consider the total number of users. So up to 50% it can survive, 50%. But here, if it is more than 33% of faulty nodes, then PBFT will not reach the consensus. In case of Ripple, if it is more than 20%, then it will not reach the consensus. And in case of the power consumption, so the proof of work needs large power because it has to solve that puzzle. And in case of proof of stake, it needs less because there are certain authorities who are decided. That means in proof of stake, what happens? The one who is having more stake, they will be allowed to mine the blocks and they are the one allowed to validate the blocks. The problem we see with this proof of stake is the one who is having more stake, they are allowed to mine. So let's say that they are taking the reward. Then what is going to happen? The one who is already having the more stake, they are going to increase their stake. The one who is not having, they are not going to get any facility to increase their stake. So it's like we can say richer is getting again richer and poorer is always in that level only. So that's the reason this delegated proof of stake has come. In case of delegated proof of stake, let's say I have the stake and I authorized someone else on behalf of me to do that validation so that he will also get that reward. So that's what the intention is. The question of issue that is richer, always richer, is going to get reduced here. And in case of PBFT and Ripple, it's negligible because there is no need to solve any puzzle. It's simply only the communication over. And scalability wise, this is good, this is good, this is, and this one is bad. And even in Ripple also, it is good. So it's like in Ripple, the nodes are grouped into, the nodes are grouped, and there is a requirement that a node can be part of more than one group. That is the overlap. So what advantage it is going to bring is the decision of one group will be brought to the next group also. That's what the advantage is. So we'll discuss the fast probabilistic consensus. So you will get some more idea about that. And application, this is for public, this is for public, and this is, and these are for only the permission network. But still, we are into the problem of consensus protocol for the permissionless network. So we can go for proof of stake or delegated proof of stake. There also we can see this power consumption is an issue, and the next issue, as we discussed, that richer will be always richer. So IOTA has come up with consensus mechanism, which is called fast probabilistic consensus. The scenario is like this. Let's say here they follow various things, so that we have to go through the complete IOTA to understand all. But let's say the connection is like this. Now, I'm not going for, that is, we are not going for the proof of work. So they are also having the proof of work called as adaptive proof of work, but that adaptive proof of work is very simple to solve. So it won't be like complex as actual proof of work that is getting used in Bitcoin or that was used in Ethereum. So what happens now? I want to reach consensus on something. What I will do is I will take that value, or it may be whatever that one I want to finalize. I will ask my neighbors whether you are agreeing with whatever the decision is. For example, the decision is yes. So I ask here, see, we should remember one thing, the consensus should come from the entire network. So now I ask my neighbor whether you are agreeing with this, yes. Let's say he say yes, he also say yes, he also say yes, he also say yes. All of them have given me the output as yes. So now it's not final. So now I know, yes, in first round it is accepted with full majority. After some time, again I ask the same question to all of them. So we cannot expect the same result, because when I ask them, they have given the response, they also ask their neighbors, and these person will ask their neighbors. So in the next round, the output may be from this level I am getting. That means they are giving here and they are giving it to this next person, and he will put up his majority here. So in the next round, it may be 0.8% I got as the right, and wait for some more time, again ask. So because by that time this is getting propagated to the next level, and the response is coming back. So this person will give the consolidated output of the decision of all these nodes, and this person will give the consolidated decision of all the nodes connected. So in this way, what happens, we don't need to solve the puzzle, and we don't need to communicate with all other nodes. So we have to communicate with our neighbors. Our neighbors will communicate with their neighbors, so it will go in rounds. So in this way, IOTA ensures that we are going for permissionless network without the proof of work or proof of stake for consensus purpose. Because as I said, they use adaptive proof of work to control or to contain the denial of service attack. However, for consensus, they are not using that. So they use simple fast probabilistic consensus, so which is extension of the simple majority consensus. So what they find an issue with simple majority consensus, let's say at time I, a person asks all the neighbors, what is your opinion? So the average opinion is collected from the neighbors for this one. If it is more than this threshold, it is considered as accepted, otherwise rejected. Then again, after some time, the next round. So the next round is T+1. So I said that I is the time. Actually, I is not the time. I is the person, let's consider. So in T+1, again, I am asking the question. When I ask the question, here you see the variable, but here we have the constant. So what is happening is like, again, we are asking in the next round, the majority says, yes, it is there. They are saying as 1 or not. If the majority is greater than 0.5, that means out of 10, let's say 6 are saying yes, 1 is agreed, then it is like greater than 0.5. So 1 is accepted in that round also. So earlier also 1, now also 1. If it is less than 0.5, we say as no, we are going to reject in this round. So, but it will be keep on going. We are not going to take the decision there. After certain number of attempts, if the same output remains for long, then only we are going to take the decision. If it is equal 5, whatever was the decision earlier, we are going to keep this. The issue they have identified is that this value is the constant value. And since this is the constant value, attacker can make the majority by colluding to bring always this 0.5, more than 0.5 or less than 0.5. So to overcome this, they introduce the fast probabilistic consensus, where here also the variable is used. This variable is computed in the distributed fashion or the decentralized fashion. So this is something like a value which is generated through the decentralized random number generator. So what the decentralized random number generator is, we know the random number generator, but the contribution comes from the multiple nodes. So that's why it is decentralized random number generator. So with this, they are reaching the consensus in the network. So it is having the scalability as well as it will be taking less computational cost. So consequently, the power consumption will be less. So this is about the consensus protocol. Now the next issue, see, if we see the blockchain implementation, the issues of applying, we can discuss in various aspects. So one is computation. Because of the consensus protocol, but as we have seen, there are various consensus protocol we can apply according to our requirement. We can reduce the computation cost also if we go for fast probabilistic consensus and ripple kind of things. Next is communication overhead. And communication overhead also, we know that we are not going to consume the bandwidth in Gbps and all. It will be only in Mbps, as I have also done certain analysis. And next is the storage. See, the blocks are keep on growing. And whenever we say that if the growth of the block stops, that means we can say that particular application is dead. The reason is, you know, the transactions are only accepted if it is committed into the block. If the block is not getting created, that means we can say the transactions are not getting committed. If the transactions are not getting committed, there is no activity happening in the application. So we can say the application is dead. So the block should keep on growing. It should never stop. And if it is keep on growing, then storage will be an issue. We have to store all the blocks, and we may not be having such storages. So there are solutions available for that. There are various solutions. Like in case of Ethereum, they have light Ethereum subprotocol. So what is this light Ethereum subprotocol is? We have seen the block has two parts, block header and the data part. They will store only block header. See, the nodes, let's consider the light node. Those nodes will store only the block header. It will not store the block data part, so that they can save the storage. And IOTA introduces the snapshot. It's like if we have the tangle, they call there as the tangle, which is the directed acyclic graph. If I don't have the storage, I can take the snapshot. Snapshot means I keep the consolidated values and accommodate the further things. That is the further transactions. And there is a Liti chain also. It stores the block in the form of tree. So here they delete the blocks. The older blocks are getting deleted so that we can save the space. So we have also proposed our model where we are also deleting, but still we are following the linear chain, not as the tree. Because in the tree, the problem is we have to set expiry time for each and every block. Sometimes what happens, the expiry time of the higher node is lesser than the lower node. So in that case, we cannot delete the node because the lower nodes will also be disconnected. So we have to keep that. So we consider we will keep only the linear chain, but in the linear chain, we divide into certain part, that is we are grouping or partitioning the blocks, and we delete the partition, we maintain the hash of it. So that's what we do. So you may see more details on this paper. So this analysis we have done. Let's assume that there is a node which is having 5 GB of storage. So it cannot occupy more than 5 GB. So we have taken traditional. So this analysis is considering Ethereum block size. So the traditional one is it stores both the block as a header as well as the data. This stores only the header. This I set hash, F set hash, and the grouping, it's like ours. We are deleting the blocks and we are maintaining the hashes. This little chain is the one which I was talking about. This light chain uses the skip graph, and this erasure code is another one based on the, it's like some kind of accumulator is getting used, and it ensures the availability always. So if we, so these are the weeks, first week, second week, 234, like that. If we see that in case of traditional one, if we store the blocks, after 2 weeks, the device will not be having storage to accommodate the blocks. In light Ethereum subprotocol, after 234 weeks, it cannot store the blocks. So it will get exhausted. So like that, for each and every analysis model, we have done this analysis. And what we say is like, we can delete the blocks and keep only the hashes, but that is also going to consume more storage. So we can delete those hashes also. So we'll be accommodating new blocks. Accordingly, the number of blocks or the set hashes will get deleted. But the problem is there are certain, even if we see in the Bitcoin paper, the first that we can say as the Genesis paper, it is written that the older transactions, very older transactions can be deleted. However, it is not getting deleted. So similarly, we are saying we can delete the older blocks. But the problem is that maybe having the transactions which are required later stage. If we delete it, then we will be losing. But we keep the assumption all of them are not going to delete. According to their storage, they are going to delete the blocks. So let's say that we want to ensure the availability also. So what we propose is like, if there are certain transactions which are not having the consecutive transactions till now, we can take this transaction and move it to the newer blocks. So we have not given the proper layout how that should be done, but this is an idea we have given that we can move it so that can be used later also. For example, even we have proposed this blockchain technology for e-health record management system. Definitely there the older records are required. So that is older transactions are required. So for those cases, if you are moving to the newer blocks and then deleting the older blocks, it will be very much useful and it can be the best fit for certain applications. And definitely when we are applying blockchain technology to any of the applications in case of research or in real-time deployment, we have to justify, because these definitely we know if you are bringing security, there is an additional overhead. So when we are bringing blockchain technology, definitely we'll be having the additional overhead. So that has to be justified. We have to see whether we can accommodate that much overhead or not. So that analysis should be done. So there was a slide which I missed in the previous session. So with this, I can conclude, which is very important. Let's say that you have an application and you want to decide whether your application needs the blockchain technology to be implemented. Because I have seen there are various research papers or the organizations, they want to use blockchain technology for their application. However, there may not be need for using blockchain technology into that application. So we have to decide whether we want to use blockchain technology or not. Because as I said, it gives the additional overhead, and accordingly we have to decide. So sometimes we will apply the blockchain technology to an application which is not required for that, and it is taking the overhead, or it gives the overhead for the application. So this is one of the flow diagram like this. There are other flow diagrams also you can refer to decide whether we can go for the blockchain technology or not, and what type of blockchain technology. So the first question we can ask ourselves is, do you need to store the state? So store the state means if our application is going to have the state change. Okay, earlier it was in one state, and then next state, then later it will be in other state. For example, update in the account balances also. And if we want to maintain those updates. So in that case, the question, if it is yes, you go for the next question. Otherwise, you can straight away decide there is no use of blockchain technology. So we don't go for that. And the next question is, are there multiple writers? If you are having only one writer in your application, that means it is centralized. So there is no need for that. Otherwise, you take the next question. It is like, can you use an always online trusted third party? For every activity, if you are bringing the trusted third party in between, then also again, no need of using the blockchain technology. So if you are not using, then take the next question. The question is, are all writers or no? If you know, in permissionless network, we don't know the people who are joining into the network beforehand. That's why it is permissionless. But in case of permission network, definitely we have an administrator and who allows the person who are only new. So let's say if you don't know the writers beforehand, then we can say like we can go for the permissionless blockchain technology. So all these questions are asked and answered satisfactorily, then go for permissionless. If you know the people already, then if you are trusting all of them, then don't use the blockchain technology. But however, you cannot trust. The reason is there is a possibility of insider attack. If no, then take the next question, that is public verifiability required. So it is like, what is that public verifiability is something, let's consider there are two operations, read operation and write operation. Write operation is the one going to update the database. Read operation is the one which is going to validate the transaction. So if I say in my application, I allow anybody to validate, however, they cannot write. So in that case, I will go for public permissioned blockchain. If I say that no, I want write as well as validation only by my known people, then we have to go for the private permissioned blockchain technology. So based on this, we can decide what type of blockchain technology we can use for our application, and then whether we want we can use or not. So it should be on the other way around. First, we have to decide whether application really needs the blockchain technology. If it needs, then what type of blockchain technology is required. So as I said already, there are different flow diagrams. So you can use those and then decide whether it is required or not, since it's going to provide or bring the overhead into the network. So with this, I stop. If any questions, then we will discuss on the questions. So now you may please ask your questions if you have any. So I could see a question in the chat box. It's written like, in case of mobile ad hoc network or VANET, can we use? Yes, blockchain technology can be used. Even we are also we have paper considering the smart transportation system. in which we say like we want to authenticate the device using the blockchain technology. That is like decentralized device authentication we are doing. Also, we could see that there is a possibility of cyber attack in the VANET. So we are trying to apply the blockchain technology so that we can ensure the prevention of the cyber attack. So how to integrate blockchain with IoT? So it's like, see, if you are talking about IoT, you have to see which application you are going to consider IoT application. So if you bring the vehicular network or smart transportation system, definitely the IoT comes into the role. And for online shopping platforms such as, yes, we can go for the blockchain technology, but Amazon, if we see, it is like centralized. In case of centralized, there is no need to go for the blockchain technology. However, if we see like Facebook and other things, okay, social network, so there we can think of the blockchain technology, and there it is always cyber attack is an issue. Any application where we use. So as I was telling that we have considered, so we have not applied, we have considered for e-health record management system for decentralized device authentication, and it can be used for supply chain management. So it can be, I know IIT Kanpur is having is built the application for the self-sovereign identity. With that only they are issuing the degrees. So like that, there are so many applications, and even they have the application for the land record management system. So that can be used for state and central government. Is it possible to combine cloud and blockchain? People are now combining because they cannot accommodate the block, so they are going for cloud, but we should ensure that it should not be a single cloud. Otherwise, it will be like again centralized. See, as I said, yes, people are using for supply chain management. So in supply chain management, it is mainly, I can say, for the delivery, that the goods are not like the duplicate or fake products. Mainly for those purposes, they use the blockchain technology. Any open source applications, we can say like toy kind of things available. Now, recently I have gone through some article. I think some organization, they are trying to build a platform where you can create your own enterprise applications, that I have seen. Otherwise, there are, maybe I cannot say as open source, but if you contact them, they may give the application. But anyway, it's up to them. Otherwise, I don't see the complete package available. So, any more questions? So, could we use blockchain in cipher physical system for malware analysis? Yes, we can use. See, when we talk about the cyber physical system, even we can say this. Yes, we have applied for the smart metering infrastructure. So we have a paper where we applied. So what we say is, we can take the smart meter into the next level. Normally, we say the smart meter will only transfer the number of units consumed. So more than that, we can say the smart meters will communicate with the nearby smart meters and share the information. Like when power goes, we normally ask our neighbors. So like this, we can say that the smart contracts can communicate. However, the security is an issue. So that's why we propose to use the blockchain technology into that. See, there was one MBA student worked with us. He has developed a model for stock market prediction. So which can be done very quickly. That's what his claim is. And even it is It can be used for the insurance, so that we can ensure that the claim is very genuine and it happens in time. See, as I was telling regarding the scalability and storage issue is now like our models also, the models are coming. We are planning to integrate our model with live Ethereum, but anyway, first we will try that in our private network, then we may propose. And regarding the scalability issue, as I have said, IOTA has that fast probabilistic consensus. So like that, the algorithm, the consensus protocol will come. Even IOTA is also considered as the right solution when we have the issue of scalability. See, when we say about the private blockchain, for example, whatever I was demonstrating as the test bed. So we cannot say the permissioned blockchain and private blockchain as same. So private blockchain, you can say you can run the permissionless blockchain implementation in private, because you don't share the Genesis file with others, so that they cannot connect to your network, and you are not sharing that details. You are running your own network. So it's like you have to run your own. So the Go Ethereum is available, which is open source. With that, you can run, or you can use our testbed to run your own private blockchain network. So I checked the testbed. Is it possible to fetch data from any? Yes, you can fetch. Whatever device you are choosing, you can fetch from all. So maybe one device or some other device not giving. So that device may not be connected properly, that we can check. So health sector, yes, definitely we have, our paper is already there on e-health record management system. We have done the detailed analysis. Any other questions? So any more?
So now most of the questions are basically they're asking very general questions, and I think many of them you have already answered, and we are getting a very wonderful feedback of your sessions, Dr. Venkatesan.
Sorry to interrupt. There is someone raised the hand.
Pardon? Raise the hand. Okay.
Someone has
so he must have raised the hand. I cannot see.
Someone, I think name is Parvati.
Parvati, just a minute. Parvati. I can't see her raised hand, but you please, you can unmute yourself and ask question if you have any.
So meantime, there is another question. Someone has asked for scalability. Can we use IO-inspired algorithms? Actually, I'm not sure about that, because I never explored in that perspective, because I cannot comment on that, because I have not done any work considering that. But I doubt how this is going to help.
Sir, I have one question. Ritu Dagar this side.
Yes. Yes, please.
Sir, how to improve your data security in cloud computing using blockchain?
What I always say is that, see, normally in a blockchain, for example, e-health record management system, we don't put the actual data into the blockchain. We put only the metadata into the blockchain. However, the actual data, it may be either in the cloud or it may be in the interplanetary file system. So which is like the third-party storage network, we can see. However, when it comes into the data security, normally I say, while we use the cloud, we should encrypt our data input. We should not put in plain format, because the data is not in our control. The cloud service providers claim that their storage is very secure because they use various layers of security. And the key comes from the trusted platform module also. But the problem is those all for the external people, but still there is a vulnerability for an insider threat. So that's the reason we should not keep the plain data. Even we use the blockchain technology which stores metadata, actual data in the cloud. We should encrypt and post the data there.
Thank you, sir.
But there are issues comes out, how we are doing the key management. So those issues are still there and research is going on. There are so many other works are already done. We are also working on it. So you can also see how you can also contribute in that area. Maybe you can join with some team and do that.
So there are no more questions, it seems. If you have some questions in your chat box, Dr. Venkatesan, you can check.
Yes, madam.
We don't see any further.
I think no new questions, all are answered. And anybody want to have collaboration with us, you are always welcome. If any other queries also, you can write to me. You are always welcome for the research collaborations. So thank you so much, madam, for your wonderful opportunity that you have given me.
It is such a great pleasure to listen to you and to your ideas. And it was 2 wonderful sessions, I must say. I am sure that participants have been deeply benefited and they have enjoyed your session. The way you were clarifying things, you were explaining things, made things so easy for them to understand. So sincerely, thank you on behalf of Asia Connect project team and IIIT DM Jabalpur. This project, Dr. Venkatesan, is running in 4 countries.
Okay.
So we have participants from 4 countries. That's the uniqueness of this project.
Okay.
Thank you so very much. Dr. Neelam, we would like to say something.
So definitely, ma'am, you have already thanked him from our side, so nothing else. Thank you so much, sir. And every time I call him, every time I mail him, he is always ready to collaborate in each of my programs. So thank you so much.